Oh, I have to say, accept. Yeah, so cubic surfaces are a very famous example of Alpeza surfaces, the smooth cubic surfaces in P3. And a famous example is the Kleb surface, which has this cubic equation. And you see a clay model here, which I think is in the University of Göttingen. There's many of these kind of models from many years ago of these kind of surfaces, very nice. And a lot is known about these surfaces already for a long time. For example, we know that over an algebraically closed field, such a surface always contains 27 lines. And any point on the surface is contained in at most 3 of those lines. And we call those points Eckert points. And if you zoom in this picture, you see all those lines. The Kleb surface is the surface where all 27 lines are real, which is nice. So you see them here. You see some Eckert points also where 3 lines intersect. And we know how all the lines intersect basically, because the intersection graph of these lines, where vertices are the lines and they are connected if they intersect, is the complement of the Schläfli graph, which you see here. So this is the Schläfli graph, and the complement is the intersection graph on these 27 lines. And there's many more results known. For example, we know that there are at most 45 Eckert points on a cubic surface. And I believe the Kleb surface has exactly 10, for example. Okay, so these are cubic surfaces. And more general, I'll talk about the Alpeza surfaces. So the Alpeza surface is a nice surface, and by nice I mean smooth, projective, and geometrically integral with an ample anticanonical divisor. So it comes with some multiple of the anticanonical divisor. It gives an embedding in some projective space. And the degree we say to be the self-intersection of this canonical divisor. The degree can be between 1 and 9, so the Alpeza surfaces exist from degrees 1 to 9. And here are some examples. So the smooth cubic surfaces in P3 are those of degree 3. The Alpeza surfaces of degree 4 are complete intersections of 2 quadrics in P4. The Alpeza surfaces of degree 2 are double covers of the projective plane that are ramified over a smooth chordic curve. The Alpeza surface of degree 1 I will get into in detail. And in general, for degrees 3 to 9, a Alpeza surface is isomorphic to a surface of degree D in PD. And this is how they were originally defined by Alpeza. In that case, the anticanonical divisor is very ample. So this just gives you the embedding right away, which also makes sense that we call the degree the self-intersection of this canonical divisor. And the Alpezas of degree 1 and 2 are kind of generalizations of this classic idea of surfaces of degree D in PD. Okay, so these are the Alpeza surfaces. Well, what can we say about their geometry? Over an algebraically closed field, the Alpeza surfaces are rationally equivalent to the projective plane in the following sense. So if we have a Alpeza surface of degree D over an algebraically closed field, then it is isomorphic to either the product of 2 lines. This only happens for degree 8. So then it's just P1 times P1, or it is the projective plane blown up in 9 minus D points in general position. And general position means no 3 points are on a line, no 6 points are on a conic, and no 8 points are on a cubic that is singular at one of them. So yeah, the Alpeza surfaces over algebraic closed fields are basically blow-ups of the projective plane, except for this one case of degree 8, where it can be either a blow-up or P1 times P1. And that's very nice, because this gives us a really easy description of the Picard group of the Alpeza surface. So again, we take an algebraic closed field, and we let X be the blow-up of the plane in at most 8 points in general position. So X is now a Alpeza surface by the previous theorem. But we exclude the weird case of degree 8 of the product of 2 lines. Then the Picard group is the direct sum of some copies of Z, where L is the pullback of a line in P2, which is not going through any of the points you blow up. And EI is the exceptional curve above the point. So the Picard group is completely described. Of course, if you blow up, you know exactly what the Picard group looks like. And moreover, if the degree of your surface is at least 3, then the lines on the embedding correspond to the classes in the Picard group that have self-intersection -1, and that intersect the canonical divisor with intersection -1. So I recall that in this case, the anti-canonical divisor is ample. So this gives you the whole embedding already, very ample, sorry. This gives you the whole embedding already. And lines on that image are exactly these classes. So in general, also for degrees 1 and 2, we call curves that correspond to such classes in the Picard group, so that have self-intersection -1 and that intersect the canonical divisor with intersection -1. We call them exceptional curves, but often we also call them lines. So in this talk, I'll probably switch a bit. I try to be consistent with exceptional curves, but for degrees 1 and 2, even though they're not really lines, we all call them lines usually. Okay, so these are the kind of the special cases in the special things in the Picard group that we talk about. And we can find all these exceptional curves using this description, just by seeing which one have self-intersection -1, etc. Of course, the exceptional curves above the points you blow up are exceptional curves, but also the strict transform on your Alpeza surface of any line in P2 through 2 of the points, any conic in P2 through 5 of your points, etc. So I won't read this all out loud, but just to say that we really have all these exceptional curves on your Alpeza surface are described by basically curve downstairs through your points in a certain way. For example, a Alpeza surface of degree 7 is the blow up in 2 points, so I get 2 exceptional curves above those points. And of course, there is one line through those points, and this gives me another exceptional curve. And this is also how these curves, exceptional curves, intersect on your surface. So you know exactly which how they intersect. Degree 6, I blow up 3 points, and of course, through every 2 of those, I have a line, and they give me exceptional curves, and they all intersect like this. So I have 6 exceptional curves. And degree 5, I blow up 4 points, and every line through 2 of them gives me another exceptional curve. So I get 10 exceptional curves, etc., etc. And this is the whole list of the number of exceptional curves. So you see that it grows quite rapidly, and at some point you really cannot draw it easily anymore, especially not how they intersect in this whole graph. So yeah, we know exactly how many lines there are on the Alpeza surface over an algebraic closed field. Okay, and now I want to talk a bit about rational points on the Alpeza surfaces, because that's how we came up with the question that where the main theorem has an answer to. So a variety is called unirational over a field if there is a dominant map from some projective space. So there is a birational map such that not birational, a rational map such that the image is dense in X. And this, of course, implies that there's many rational points on your surface. And for the Alpeza surfaces of degree at least 3 over a field that do have one k-rational point, we know that they are unirational. So this was first proven by Segre over Q for degree 3, and then Manin did it for degree at least 5, I think, for any field, and then and for degrees 3 and 4 only over certain fields, and then Collard finished the degree 3 case, and Piropan finished the degree 4 case. And for the Alpezas of degree 2, we also have a result. So recall that these are double covers of the plane that are ramified over a smooth chordic. And by a theorem from 2014, we know that if such a surface contains the k-rational point, which is not in the ramification locus of that double cover, and which is not contained in the intersection of 4 lines, then it is unirational. And I highlighted the not contained in the intersection of 4 lines to show that these intersections and these the lines and how they intersect, they come up sometimes in these kind of results. So you need certain things not to happen in order to have certain results. And we'll see that now more. Yeah, so this is, yeah, for the Alpeza surface of degree 2 and 3, 2 and up, we basically have results on unirationality with this one extra condition for degree 2. So what about the Alpezas of degree 1? What do we know? There's one result about unirationality by Collard and Mella from 2017. It says the Alpeza surface over a field with characteristic not 2 that admits a conic bundle structure is unirational. And for unirationality, you only have to look at minimal surfaces because this is invariant on their birational maps. So minimal Alpeza surfaces of degree 1, oh sorry, this should be of degree 1. They have Picard rank 1 or 2, and the surfaces in this theorem are the ones with Picard rank 2. So for that class of the Alpeza surfaces of degree 1, we know that they are unirational over a field of characteristic not 2. But apart from this class, the question is really wide open. So it's not known if there is an example of a minimal Alpeza surface of degree 1 with Picard rank 1 that is unirational, or if there is an example of such a surface that is not unirational. At least people are not able to prove either or for these kind of surfaces. So in some sense, we don't really know yet what direction to hope for also. So for the Alpeza surface of degree 1, this is really considered a very hard question, but there is a slightly easier question where we do have some partial results, and that is the density of rational points. So if you have an infinite field, then unirationality implies that the rational points are dense. And here we have some partial results for various families of the Alpeza surface of degree 1 or various fields, etc. Barilli Alvarado in 2011, and then there was a series of results building on each other by Ulas, Togbay, and Jabara in 2007-2012, and then Van Lyck Salgado had a result in 2014, and then joined with Julie Desjardins, we have a preprint that we submitted earlier this year with a result on density of rational points. So to summarize about the rational point story, just because it's a lot of information. So if you have a Alpeza surface of degree D over an infinite field, and we assume there is one rational point, then for degree at least 3, we know it's always unirational, and therefore also the rational points are dense. For degree 2, we only know this under a condition that this point is outside a closed subset, which is this ramification curve and the intersection of 4 lines. Of course, in that case, the Zariski density is implied. And for degree 1, we only know it for the ones that have Picard rank 2, if your field is also not characteristic 2. But Zariski density we know for a bit more there. So this is for several families. And that's kind of the state of this unirationality story and density for the Alpeza surfaces. And I want to zoom in a bit on these last 2 results that I mentioned here to say how these lines and torsion points start playing a role. So for that, I have to explain a bit about the geometry of the Alpeza surface of degree 1. So one very convenient way to view them is that they're isomorphic to a smooth sextic in the weighted projective space with weights 2, 3, 1, 1. With these coordinates, so x has weight 2, y has weight 3, and z and w have weight 1. So this is then a smooth weighted sextic. And the AIs are homogeneous polynomials in Z and W of degree I. And the linear system of the anticanonical divisor defines a map, which is basically just projection on the Z and W coordinates. And as you can see, this is defined everywhere, except of course, when these are both 0, and that's exactly in 1 point. So this linear system has 1 base point. And when we blow up this base point, we get an elliptic surface. So this base point O now becomes a section on your, so yeah, you get an elliptic surface because you really have a section also. And the 240 lines on X correspond, if you blow up this point, they correspond to 240 sections on this elliptic surface that are disjoint from this base section, from the 0 section. So, okay, how do the results talk about these elliptic surfaces? So now we take an Alpeza surface of degree 1 again over an infinite field with characteristic not 2 and 3. We have this corresponding elliptic surface when you blow up this base point of the anticanonical linear system. And we assume that there is a rational point. So P is a rational point on the Alpeza surface. Then Van Lyck and Salgado proved the density of the set of rational points under the condition that y0 is non-zero. and several conditions depending on the order of P on its fiber. So of course, P has an image on the fiber of this elliptic surface after blowing up, and their conditions depend really on the order of P on this fiber and also of the number of exceptional curves that intersect in P. So there, the order is already a bit related to the number of lines intersecting a point. And they also give several examples for points P for which their method would not work. Of course, there can still be other points on the surfaces for which the method works, but they just say with these kind of points, the method fails. And in all these cases, the points that fail are contained in at least 6 lines, exceptional curves, and also they're always torsion on their fiber. So downstairs they are contained in many lines, and upstairs they are torsion on the corresponding fiber. And in the result with Julie Desjardins, we proved the density under these conditions for a special family of Alpeza surfaces, where Z0 and W0 cannot be 0. And this point has to be on a smooth fiber and be non-torsion on its fiber. So often you want conditions like non-torsion because of course then you have very many points, but this seems to somehow coincide sometimes with being contained in many exceptional curves. So this is again the picture bit. So here we have our Alpeza surface X. We have the point O that we blow up, that becomes a section. And this point P lies on some fiber upstairs. And the order of the point on this elliptic curve is usually contained in conditions about density. Okay, so if we take it up at surface of degree 1 with the corresponding elliptic surface, then these previous results and the examples given lead to the following question. If a point on X is contained in many exceptional curves, where many, of course, is very vague, is it then torsion on its fiber? Because this seems to coincide often. Moreover, another reason why this is is an idea that this could be true is that Kuwata proved a similar result for the Alpeza surface of degree 2, where many equals 4. So the Alpeza surface of degree 2, you should blow up 2 points to get an elliptic surface. And he has a construction where he does this, and he shows that anytime that 4 exceptional curves intersect in a point, that point will be torsion on the corresponding elliptic surface. For the Alpeza surface of degree 2, 4 lines is also the maximal number of lines that can intersect. So it's kind of the boundary situation. But this all suggests that there might be a similar result there for the Alpeza surface of degree 1. And that is our main question. And the main theorem of today is that if a point on the Alpeza surface is contained in at least 9 exceptional curves, then it is torsion on its fiber. So this is an answer to this question. If you take many to be 9, then yes, that is basically what the theorem says. And moreover, joined with Julie Desjardins, we found examples of points that are contained in 7 exceptional curves that are not torsion on their fiber. So we know that being contained in 7 exceptional curves does not guarantee torsion upstairs. 9 does guarantee torsion upstairs, and of course 8 is still a question. And at the end of this talk, I will say a bit how we are tackling that at the moment. And in the rest of this talk, I want to prove this, of course. The main ingredients are the Mordell-Well group of the elliptic surface, the height pairing there, but also the configuration of exceptional curves on the Alpeza surface. And I will talk a bit about this open case. Yeah, are there any questions so far?
So 9 is the maximal number of the -1 curves, which contains the 1 point. I mean the fixed point.
No, so I will get to that with in a bit, but actually more curves can intersect. So you can get, depending on the characteristic of your field, you can get up to 16 curves that intersect in characteristic 2. So in outside characteristics 2 and 3, there are at most 10 exceptional curves intersecting. So this is almost the boundary, but not, yeah, it's not the maximum, which is also different than from the Alpeza of degree 2 case. Yeah.
All right. Thank you.
Are there other questions so far? Okay. Okay, so how would you first think? So one idea that some people, when we thought about this question, told us like, oh, this could be an idea, is looking at this more Well group of the elliptic surface. So the 240 lines on your Alpeza surface are sections, as I said before, on the elliptic surface, and they form a group there, the more Well group of the elliptic surface. And for the Alpeza surface of degree 1, or elliptic surfaces coming from the Alpeza surface of degree 1, this more Well group is torsion free and has rank at most 8. So let's say that we have at least 9 exceptional curves that intersect in a point on your Alpeza surface. Then they correspond to n sections upstairs. So here's a picture of that. If I have, for example, 4 exceptional curves intersecting in P, then upstairs you have 4 sections, and of course they all go through P on this fiber. And since the more Well group has rank at most 8, there must be a linear relation between 9 or more sections. So there are integers such that you have this linear combination adding up to 0. And specializing to the fiber, of course, on the fiber, they are all equal to the point P. So then you have actually some relation, something times P is 0. But of course, it's not clear that you can take that this does not sum up to 0. So the goal is actually that we should show that there exists, you can choose these A1 to AN such that their sum is non-zero, because then you really have a torsion point P. And to do this, we use we really look at these configurations of lines, and we use all the possible configurations of sets of at least 9 intersecting reflectional curves, and we really study case by case, basically, as I will explain now. Okay, so let's look at the configurations of lines on the Alpeza surfaces. I gave a brief overview of all the Alpeza surfaces again, because for higher degrees, it's actually quite nice and easy to describe. So the intersection graphs of the lines on the Alpeza surfaces are known. For degree 5, it's actually up to degree 4, I drew them before, right? Or you can just draw them by hand. Degree 5, it's 10 lines, and their intersection graph is the Peterson graph. And degree 4 is 16 lines, and their intersection graph is the Klebs graph. And degree 3, I also showed before, the 27 lines intersect as the complement of the Schläfli graph. And for degree 2, it's not easy to draw, but you can describe it quite nicely. So there's 56 lines, which, as I said before, they're exceptional curves and not really lines in this case, but I use the words a bit interchangeably. And any line of those 56 intersects exactly one other with multiplicity 2 and 27 other lines with multiplicity 1. These 27 do not intersect the one that it intersected multiplicity 2. And these 27 form again the complement of the Schläfli graph. So I drew a little picture. For every L, for every line, there's exactly one that it intersected multiplicity 2, L prime. There's exactly 27 that it intersects with multiplicity 1, and they do not intersect L prime. And these 27 from the Schläfli graph. So also from this, you can see that the maximal number of intersecting lines is 4, because we know that here the maximal number is 3, and there's at most 1 that intersects 3 such exceptional curves. So 1 point is contained in at most 4 lines. And we also know that this happens always outside the ramification curve if you see the Alpeza of degree 2 as a double cover of P2. For degree 1, we have way more lines, 240 exceptional curves. So let X be a Alpeza surface of degree 1 with canonical divisor Kx. We distinguish 2 cases here. So the linear system of -2 times the canonical divisor induces a double cover of a cone in P3, which is ramified over a smooth sextic. And in a result, together with Ronald van Luik, my PhD supervisor, we proved that a point on the ramification curve of this double cover is contained in at most 16 exceptional curves if characteristic of your field is 2, and at most 10 otherwise. And a point outside the ramification curve is contained in at most 12 exceptional curves if the characteristic is 3, and at most 10 otherwise. So the interesting thing here is, well, one of the interesting things is that this shows that unlike for all other degrees Delpezzo surfaces, the upper bound given by the intersection graph is only sharp in characteristic 2. So if you look at the intersection graph on the 240 lines, how do they all intersect each other? Of course, this gives an upper bound for the maximal number of exceptional curves that can actually go through a point on the surface, because they should all intersect each other. And for all other Delpezzo surfaces, this upper bound is sharp. So for the Schläfli graph, it was 3. And for Delpezzos of degree 2, this was 4. But in this intersection graph on the 240 lines, there are sets of 16. There's fully connected subgraphs of size 16, but they can only 16 exceptional curves can only intersect in a point in characteristic 2. So actually, almost never do you find 16 exceptional curves that intersect in a point. So this is really a bit of a more difficult case than the other Delpezzo surfaces. Yeah, and how did we do this? So I want to say a bit about these intersecting exceptional curves, because we will use this later too. Let I be the set of these 240 exceptional curves. Then there's a map from I to the orthogonal complement of the canonical divisor within the Picard group of X, sending an exceptional curve to the sum of the curve plus the canonical divisor. And this induces a bijection between these 240 exceptional curves and the root system E8. And as a nice consequence of this bijection, we find that the group of permutations of the 240 exceptional curves that preserve the intersection pairing is isomorphic to the Weil group. So we have a very nice description of the basically the automorphisms of these set of exceptional curves. And if we now look at the root system, so let gamma be the weighted graph on this E8 root system, where the weights are just the inner products. So vertices are the roots in the root system, and weights on the edges are the inner products of two roots. And then if you take a set of weights, you take only a sum of the weights that are possible. We define gamma C to be the subgraph consisting of all 230 vertices, but only the edges with the specific weights. Then in another paper with Ronald van Luik, which was published this year, we study the action of this Weil group on this graph gamma and on these graphs gamma C, and we show a lot of results on the action of this Weil group on subgraphs, etc., transitivity results. But as a result, one of the things that's in this paper is that we have for each C, so for each subset of the possible weights that can occur, we have a list of all orbits of maximal cliques in this graph gamma C, orbits under the action of the Weil group. So by clique, I just mean a fully connected subgraph. So we have a lot of information about how these exceptional curves can intersect, because they are one-to-one with the roots, and we have this whole information about how the graph on the 240 roots, all the cliques in this graph basically. And here's just a part of this big graph. So as I said before, you cannot really draw it, but these are some of the results that we found. Like for example, if you take one root fixed, then there's exactly its negative root, which it intersects with multiplicity of the inner product is -2. There's 56 roots that with inner product -1. There's 56 with inner product 1, and there's exactly 126 roots that are orthogonal to this first root. And for each of those 126, there are exactly 60 again that are orthogonal, etc. So this is like a small attempt to draw the graph on the 240 roots with all their intersection multiplicities, but of course you cannot really do this in a very visible way. So this is just part of it. And as I said before, the nice thing is that this gives us a lot of information, all the information we need about intersecting exceptional curves, because you have this bijection. So you can just change the weights and you have the same result for exceptional curves. So as you see, every dot product of roots corresponds exactly to an intersection product of exceptional curves in the Picard group. So this is how we got this whole configuration of lines through the root system. Okay, and knowing all this, I can go to the proof of the main result. So how can we use all the previous things that we said? So if we have at least 9 exceptional curves on the Alpeza surface, when we assume that they meet in a point, we want to show that this point is torsion on the fiber of the corresponding elliptic surface. Well, one thing to notice is that I said before that this linear system of -2 times the canonical divisor induces a double cover of the Alpeza surface of a cone in P3. And if you're on the ramification curve of that double cover, then you're true torsion on your fiber of the elliptic surface. And this you can see quite easily actually also from the description of the Alpeza surface as this smooth sextic. Yeah, it's basically the branch points are the ones that are then true torsion on the fiber. So for our theorem, we can already assume that P lies outside the ramification curve, because if it's on the ramification curve, then you're done basically. Now, using the theorem that I showed before about the maximal number of exceptional curves that can intersect in a point, we said that if that point is outside the ramification curve, then it is at most 12, which happened in characteristic 3. And outside characteristic 3, it was actually at most 10. But so in general, we know that if P is outside the ramification curve, then this N must be at most 12. So there's at most 12 exceptional curves going through P. And then one remark is that we can go through all sets. So if we just want to do it case by case, just to see which, if I take these curves, is the point torsion, etc. We can go through all sets of intersecting lines up to conjugation by the well group, because if I have E1 to En that intersect in the point, and I have also F1 to Fn, and these sets are conjugate under the action of the well group, then this gives me an automorphism of my Alpeza surface. So they intersect in a point if and only if the other N intersect in a point, and this point will be torsion if and only if the other point is torsion. So we can really go through all sets of intersecting lines up to conjugation by the well group. And then we look at the result I just mentioned, the paper where we studied this whole action of the well group on the E8 root system, which also then gives us results about the 240 exceptional curves. And there we show that up to conjugation by the well group, there are only 11 maximal sets of size 9, there is 6 maximal sets of size 10, and there's 1 maximal set of size 12. So what do I mean by that? There's by maximal set, I mean in this graph on the 240 exceptional curves, there are only up to conjugation by the well group, there are only 11 maximal fully connected subgraphs of size 9, and there are 6 maximal fully connected subgraphs, so they all pairwise intersect of size 10, and there's exactly 1 of size 12. So there's actually only 18 sets of intersecting lines to check. So these E1 to En are always contained in one of these 18 sets, basically, up to conjugation by the well group. Okay, and the next ingredient we need is the height pairing on the Mordell-Well group. So I said before that the sections of the elliptic surface, they form a group, the Mordell-Well group, and this comes with the height pairing, which is symmetric and bilinear. And here's some facts. So in the case that this elliptic surface comes from a Alpeza surface of degree 1, then if something has pairs to 0 with itself, then it is 0. So these are sections in your Mordell-Well group. So if they pair with 0 with themselves, it's a 0 section. And moreover, it links very nicely to this E8 root system. Namely, if I have 2 exceptional curves on the Alpeza surface, and I have the 2 corresponding sections of the elliptic surface, then the height pairing of S and T is 1 minus the pairing of the exceptional curves in the Picard group, so just the intersection number in the Picard group. And this is the same as the dot product of the 2 roots. So every exceptional curve corresponds to a root in the E8 root system, because we have this bijection. and I can just get the height pairing of these two sections by looking at the dot product of the roots corresponding to E and F. And that's very nice because in this paper where we studied the wild group and the E8 root system, we have everything in terms of these roots. So we know all these height pairings basically of all the sections coming from exceptional curves. So how do we use this? If I now have the n sections that correspond to these exceptional curves, so I took n exceptional curves that went through a point on the Alpeza surface. If I take the corresponding sections of the elliptic surface, and I take M to be the height pairing matrix of these sections. So yeah, the height pairing of each pair. Then if I have a vector in the kernel of this height pairing matrix, then since this height pairing is bilinear and because we have this first fact, you can write it out and it follows that the sum, this linear combination of S1 to Sn equals 0, is the 0 section. So this looks a lot like what we want. And as I said before, we want exactly to find such A1 to An that don't sum up to 0, right? Because then if you specialize this to the fiber of P, since they all go through the point P, then this would just mean that A1 plus An, the sum of all the AIs times P is 0, but we wanted that sum to be non-zero. So the goal is to show that there's a vector in the kernel of M that does not sum to 0, and then we're done. Okay, so now knowing all this, we can prove it. So recall we took n at least 9, and we took n exceptional curves on the Alpeza surface that all went through a point outside the ramification locus of the double cover of the cone. And we took S1 to Sn the corresponding sections on the elliptic surface with the height pairing matrix M. And then we claim that this implies that the point P is torsion on its fiber on the elliptic surface. Okay, well, how do we prove this? The set of n exceptional curves is contained in the maximal set of intersecting exceptional curves. Yeah, because either, and by maximal I mean that there are no other exceptional curves intersecting every of the curves in your set. So either itself it's already maximal or it's contained, of course, in the maximal set. As we said before, there are only 18 possibilities for such maximal sets, which we found from this graph on the root system. And therefore 18 possibilities for the gram matrix of the roots corresponding to the elements in the set C. So the gram matrix is just the dot products of any of the two roots. So we know for each of these 18 sets the gram matrix, and we can compute the kernel. And then we find that each kernel contains at least one vector whose entries do not sum to 0, which is what we want, but also with zeros outside the entries corresponding to E1 to En. So a priori, this set C is bigger than this set E1 to En. So the kernel has a vector of longer length, but we always find, no matter what the E1 to En, what these indices are, we always find a vector that is 0 outside those indices. And that gives you then a vector in the kernel of M. So really the height pairing matrix of these n exceptional curves. And those entries not sum to 0. And then we find, as I said before, that this linear combination of sections is 0, restricting to P gives exactly this equation, which we saw before. And P is torsion of order M, where M divides now this number. And since we found this to be non-zero, it's really a torsion point. So this is basically what we wanted in the beginning, to find such a relation such that it doesn't sum to 0, and then we really have a torsion point. And yeah, really, we just did this case by case in some sense, right? We just really checked all sets of these exceptional curves and just checked their height pairing matrix, which is equal to the gram matrix of the corresponding roots, etc. Okay, but that proves the main theorem. And of course, the question is now, well, if at least 9 exceptional curves guarantee a torsion point, how many lines can go through a non-torsion point? And together with Julie Desjardins, we found an example of 7 lines through a non-torsion point. And this is nice because it's just very explicit. Let X be the Alpeza surface, which is the blow up of the plane in these 8 points. So you can check that these points are in general position. So if you blow them up, you get a Alpeza surface of degree 1, since you blow up 8 points. And then these are 7 curves in P2. So they are 4 lines, the line through Q1 and Q2, the line through Q3 and Q4, and Q5 and Q7 and Q8. So these are 4 lines. And 2 cubics that are the cubic through all points except the second point, which is singular in the first point, and the cubic through all points except the fourth point, which is singular in the third point. And finally, we take the quartic through all points, which is singular in these 3 points. So these last 2, of course, maybe you remember that the lines through 2 of the points gave exceptional curves upstairs on the Alpeza surface after blowing up, but also such cubics and such quartics also give exceptional curves on the Alpeza surface after blowing up. So these correspond to 7 exceptional curves on X. And moreover, you can again quite easily check that all these 7 curves in P2 go through this point 0, 0, 1. So this means that on my Alpeza surface, I have 7 exceptional curves that go through a point corresponding to this point Q. The fiber of, so now we know something on the Alpeza surface that we have 7 exceptional curves going through a point, but we blow up a point to get the elliptic surface and we want to look at the fiber of this point P. But again, we can do this in terms of P2. So the fiber of this point is actually given by the cubic through these 9 points. So the vibration, the elliptic vibration is given by the linear system of cubics through these 8 points. And then the fiber of P is exactly the one that goes through the point that corresponds to P. So we can, again, easily find an equation for this fiber. And this is a cubic curve, and we can check that P is non-torsion on this fiber. So that's very nice because that almost solves the question of how many lines do you need for torsion. So it's not 7, it's at most 9. But what about 8 lines? So the final question that we're still working on now is if a point on the Alpeza surface of degree 1 is contained in 8 exceptional curves, is it torsional on its fiber? Is it guaranteed to be torsional on its fiber? And what we're doing currently is with Magma, we computed all the sets of 8 intersecting exceptional curves. So 8 exceptional curves that are all pairwise intersecting, up to conjugation by the Well group again, because you need again 1 representative of each orbit if you want to do a case-by-case study. And there's 47 of these orbits. So this took, I believe this was 2 weeks to compute with Magma or something. So this is quite a big computation, but it was a bit of brute forced approach because we didn't really know how to tackle it otherwise yet. So we found these 47 orbits. And then you can check these gram matrices again. So the inner products of the corresponding roots. And for 32 of these orbits, the corresponding gram matrix has a vector in the kernel, which does not sum to 0. So similar as the proof that I showed before, if these 8 curves would intersect, they would intersect in a torsion point because you have a relation that does not sum to 0, and specializing to the fiber would give again a torsion relation. So that is nice. You can eliminate already 32 options. And then we found for 2 of the remaining 15 orbits, we show that even though these are sets of pairwise intersecting exceptional curves, these 8 curves could never go through the same point. So they all pairwise intersect, but they cannot go through the same point on a Alpeza. For the following reason, each of these orbits has a representative, so a set of 8 exceptional curves that contains these 4 lines. So these are again the lines through point 1 and 2 and 2.3 and 4, etc. These are the 8 points that you blow up, and you have these 4 lines. and the 3 cubics, similarly defined as before, where this is the cubic through all 8 points except the second one, which is singular in the first one, etc. So each of these 2 orbits has a set of 8 exceptional curves containing 4 lines and 3 cubics. And you can show this, again, we did with magma, that there's no 8 points in P2 in general position, such that these 7 curves can go through can all go through the same point. So they could all go through the same point, but then you would see that the 8 points are not in general position anymore. And of course, this cannot happen on your Alpeza surface. So we eliminated 2 more sets of 8 exceptional curves because they could never go through the same point. But there's 13 orbits remaining. And yeah, we are currently trying to, of course, either find an example of 8 exceptional curves that go through a non-torsion point, or eliminate these by similar means as the one before, where you can show that they cannot go through a point. But yeah, this is where we currently are. So this is to be continued. Yeah, and this is what I wanted to say today. So thank you very much for your attention.
Okay, so thank you very much. Nice talk. So any questions, comment?
May I ask a minor question? Maybe not on the main topic of the talk. So you mentioned the bounds for the number of lines passing through a point, like 10 and 12 and something, and which depended on characteristic. So are these sharp bounds, or is just some bound from above?
Yes, no, this you mean, right? Yeah, we show that they are, we have examples of all of them except characteristic 5. So in characteristic 5, I think we found at most 8 lines so far. So yeah, so they're sharp everywhere, and maybe also in characteristic 5, but we don't have an example yet there.
And how do you present examples? You just guess the blow up, the points on the plane which you have to blow up? Or?
Yes, I have to think for a second because they're a bit. Yeah, so for finite field, like for finite characteristic, we just yeah, you just randomize points in general position. Oh no, sorry, of course, because so we have this big graph, and in this other paper where we have representatives of certain cliques so we know kind of in P2 which type of curves should intersect for this. So sorry, just by looking at intersection numbers of the exceptional curves, you know which type of curves in P2 should intersect. So as I also showed at the very end, for example, we know that it has to be 4 lines with 3 cubics, you know, through the certain points. So you can just, if you start with 8 points in general position, so you can choose already 4 in general position, and then you have parameters for the others, you can kind of try to find such that these lines go through a point and kind of force it. Is this too vague? Does it answer your question?
Yeah, sure.
Okay, so any other questions, comment? I have one question. Can you play the same game with your 2 points? I mean, you have 2 points on the same fiber, same elliptic fiber. And then like you split this exceptional curves in 2 groups. One group passing through the 1 point, and the other groups are passing through the other points. And then like
and then to see if they're both torsion or something.
Some of this 2 point is the torsion or not, like these kind of questions.
Yeah, that's an that would actually be an interesting thing, because we sometimes do have that we're now trying to find examples of 8 lines going through points. We sometimes have this problem that they go, for example, not through 1 point but to 2 points, and we never actually thought of then checking what they do on their fiber. But yeah, I guess, I mean, I think in theory you can do the same thing. You just have to see when do things go through 2 different points and then check their order. And you can play the same game in the sense that we have all these sets available, like we know which sets to check more or less. And then you just have to find geometric examples, really. Yeah, I think it's a nice idea, actually. Thinking.
All right. Any other questions, comments? Okay, so I think it's more or less that's it. Okay, if not, then let's thank speaker again. Thank you very much. All right.
Thank you. Thanks for the invitation.
All right. So you have a good day, and
Yes,
thank you for coming for everybody. Okay.
Thank you.
All right. Bye.
Bye.